Right, welcome to the last talk of the conference. I'm Venkatraman, a PhD student at Carnegie Mellon University. I'm presenting work on heuristic search on graphs with existence priors for expensive to evaluate edges in collaboration with my advisor Maxim, Likhachev. All right, so the motivation for this work is high-dimensional robot motion planning. So let's say we have a mobile manipulator like the PR2 robot, and we wanted to get from point A to point B in a kitchen-like environment so it can pick up some object. Now, this is a very high-dimensional planning problem. The robot can move around. It has an arm with which it can pick up objects. And so we're planning for all of these degrees of freedom. And then the way we represent the problem is as a graph search problem in which each vertex in this graph corresponds to a robot configuration, and edges correspond to small motions the robot can take. Okay. And this is an implicit graph. We're not going to construct the whole graph up front because that's a lot of states and it takes a lot of memory to store. So in these problems, one of the main bottlenecks in doing heuristic search is the time it takes to do edge evaluation. Now what I mean by that is when we expand a state and generate successors, which are these small motions, now we have to do expensive collision checking between the robot's full geometric model and the environment, which is represented as a set of points. And that tends to dominate a lot of the motion planning time. And so in this work, we want to see how we can address that. Right. So the key observation in this work is that we can get probabilities or guesses for whether an edge might be in collision or not before doing expensive collision checking. Now, how is that possible? So here I'm showing you a top-down view of this environment, and then the colors represent the distance to the closest obstacle. Now, for example, if the robot is in a region which is far away from the obstacles, then we know that the likelihood of small motions being in collision is very small. At the same time, if it's close to an obstacle, then we really have to do fine-grained collision checking, and then the probability of collision could be large, right? And then these probabilities of collision are directly related to the existence probabilities of those edges. Now, if there's a high likelihood of collision, then the probability of that edge being existent in the graph is very small. Now, one thing which I want to make clear is that these collision probabilities are not execution probabilities. These are probabilities or priors for the edge existence. We can always run full collision checking and find out if that edge is actually present. But somehow we want to now make use of these edge existence priors to speed up planning. Right. Now, like in any other planning problem, there are two conflicting objectives. So one, we want to find solutions very quickly, and in the other, we want to find solutions that are close to optimal. Right. And one way we could go about finding solutions really fast with these edge existence priors is we could ignore all the edges with our low likelihood, and that way avoid doing a lot of collision checking. But on the other side, that could end up leading to really suboptimal paths. And if we wanted optimal paths, we could run A star, evaluate all of the edges as we generate them, and that can take a really long time. And this is a problem which several people have looked at in the past, the one of expensive collision checking. Specifically works like lazy weighted A star or lazy shortest path. These works try to defer as many edge evaluations as possible in the hope of speeding up planning time. And similarly, there has been a recent work where the authors have tried to minimize a cost, which is a combination of path length and collision probabilities. However, in this work, our formulation is one of an anytime algorithm because we have these conflicting objectives of fast and good quality. And the specific anytime algorithm that we choose is one of a bound optimal anytime algorithm. And what I mean by that is we want to design an algorithm that minimizes the expected suboptimality bound of the solution when the algorithm is interrupted. So this expectation is over randomness in the algorithm's interruption time. Okay, so before I go into the details, I'll give you a quick overview of the contributions. So what we have is a general graph in which certain edges have existence priors. So for example, here edge A and B may or may not exist, and we have a prior for their existence. But at the same time, we can always verify whether they exist by doing this time-consuming collision checking. Right. So we have this graph with edge existence priors, and our goal is to find solutions quickly. Right. And so there's a two-part approach. In the first step, we are going to quickly find a lot of paths from start to goal without doing any expensive collision checking. And that part is called expected shortest path star. And once we have the set of paths, then the question is how do we go about evaluating the edges in those paths? And that's the part of anytime edge evaluation. Now there's also optionally a chance to interleave both of these two methods. So let me jump into the first part of this algorithm, which is the expected shortest paths. So we have this graph, edges A and B may or may not exist, and we want to quickly find a set of paths. All right. So what are the possible paths that could come up? Now, if edge A existed, then the shortest path would be directly from start to goal. But if A did not exist and B existed, then the shortest path would be this one. And if neither existed, then we'd have to go all the way around, right? So what we really have is a shortest path for every possible realization of this graph. And so one way we could compute all of these paths is by enumerating all of the possible instances and running an A star. But that's not going to be a very computationally efficient algorithm. And to develop an efficient algorithm, the key observation is this particular statement here. So the number of unique shortest paths that we would get across all of these instances is typically much smaller in number than the number of possible instances. So what I mean by that is, if edges A and B both existed, then the existence of B does not really matter. This is going to be the shortest path in both of those cases. So we want to make use of this observation to develop a more efficient algorithm that computes all of these different paths. And the algorithm builds upon this idea of an augmented state space. So let's consider a particular vertex in the graph, x, and we define an augmented state as an appendment of x with a set of edges that are being traversed in getting to that state. Now, for example, we could find a path that goes from start to x that traverses edge A alone, and that would correspond to the augmented state x comma A. Or we could have a path that goes through B, and that would correspond to xb. Or we could have a path that goes through A and B, and that corresponds to the state xab. Or we could directly go to x without traversing any of the stochastic edges. So for every possible vertex in the original graph, we could have up to 4 different augmented states. So now the claim is that once we have this augmented state, we can simply run A star on this augmented graph to generate all the possible shortest paths that might come up. And so there are some modifications we need to do as well. So the start state for A star is going to be the original graph state x start appended with the empty set. And then we run the search until x goal comma empty set is about to be expanded, or if the open list is empty. And then the key computational efficiency condition we are going to use is this notion of state dominance. Just like how in A star a state dominates another one if its g value is smaller, we are going to say that a state dominates another one if both of them correspond to the same underlying graph state, and if the g value is smaller, and if the edge set traversed is a subset of the other one. To give you an example, in that particular vertex x, xa dominates xab because it's shorter, and the set A is smaller, is a subset of set AB. So we would never have to generate xab. And so that's where we're going to get all the computational efficiency from, and hopefully not have to enumerate all of the exponentially many augmented states, right? And one other thing we're going to do as we run A star is every time we expand a state that corresponds to the original x goal, we are going to save that to our list of candidate paths to the goal. And so that's it. So this gives us a way to generate all of the unique shortest paths that might come up in any realization of this graph. And as a consequence, what we can also do is compute the expected shortest path cost. And then the efficiency theorem we have in the paper is that the number of expansions you make corresponding to a vertex is bounded by how many stochastic edges are there in getting to that particular state in the graph. All right, so that's the first part where we computed a set of paths without doing any collision checking. So we still don't know if those edges A and B exist. And what we want to do next is, given these set of paths, go about evaluating the different edges, right? And so let's say we have 4 different paths in the graph, P1, P2, P3, and P4, and they have costs 5, 150, 30, and 50, right? And path 1 goes through 2 stochastic edges, 0 and 1. Path 2 goes through no stochastic edges, so it's completely deterministic, and path 3 goes through stochastic edge 2, and path 4 goes through 3 and 2, right? So now one thing to note is that if we are stopped here, if the algorithm is terminated, we can always return path 2 as a solution. Now it's feasible and can be executed by the robot. And we can also compute the suboptimality bound of this solution. And how's that? So we are returning a solution of cost 150, but the best possible solution could be this one. And so the bound on our solution is really 150 by phi, which is 30. So the thing to note is at any point of interruption, we can compute a suboptimality bound on the algorithm. And as I mentioned earlier on, the goal of the anytime algorithm is to minimize this expected solution suboptimality with respect to randomness in the algorithm interruption time. All right. So we are going to formulate this problem as a Markov decision problem, and where each state in this MDP is going to be a vector of length number of stochastic edges. So each element of this vector can have three possible values, which is either unevaluated, could be evaluated and valid, or evaluated and invalid. And then the actions in the MDP correspond to evaluating one of those stochastic edges. To give you a quick example, let's say the initial state is all of the 4 edges being unevaluated, so they are marked dash. And now we could go ahead and evaluate edge 0, and with probability 0.4, that edge will exist. And so in the MDP, we would end at the state 1 and 3 dashes, right? Because we haven't yet evaluated edges 1, 2, and 3. And now with probability 0.6, that edge might not exist, and we would end up at this MDP state. And again, we could do this for different edge evaluations. So this is the MDP that we have. And the thing that we don't have yet is the policy for the MDP. What is the cost function that we want to optimize? And as I mentioned, we want the policy to minimize this expected suboptimality bound, where the expectation is over the algorithm interruption time. And for now, we'll assume it's uniformly drawn from 0 to capital T. So the key result in the paper is that doing this policy optimization, so one thing I want to add is this is graphically equivalent to minimizing an area under the suboptimality bound curve. So different policies would lead to different suboptimality bound profiles. And what we want is a policy that has the least area under this curve. And the key result in the paper is that we can show this policy optimization is exactly equivalent to minimizing the expected sum of future costs to go for different state action costs defined specifically as follows. And the key thing to note here is that while the first expectation is over the algorithm interruption time, the second one is only over stochasticity in the edge evaluation. So what we really have is the usual MDP, or rather a SSP, with a particular choice of cost function. And if you go ahead and solve that, the optimal policy is guaranteed to minimize the expected suboptimality bound for a randomly chosen interruption time, uniformly chosen. Right. And so to give you an example for this particular example graph, the optimal policy looks as follows. At the first step, we would evaluate edge 2, and if it turned out to exist, then we would evaluate edge 0, and if that existed, we will evaluate edge 1, and basically we stop there because this is the best path, right? And so that's the algorithm. So we put these two together in the motion planning problem. So the first experiment is on the Levendorf motion planning for the PR2 robot. So these 11 degrees are made up of 3 for the base, x, y, and orientation, 6 for the end effector of the robot, 1 free angle, 1 for the torso. And as I mentioned before, the edges in the graph correspond to small motions the robot can execute. So we compare with a lazy weighted A-star algorithm on 100 different random start goal pairs, and we use the MHA star search for both of those approaches. So in this table, I'm showing you a comparison of 2 variants of our algorithm, A1 and A2, with the lazy weighted A star. And a trial is counted as successful if we found a solution within a 2-minute timeout. And so we also compare the solution cost and the planning time for each of these methods. So the key result is that we are able to get solutions faster and consequently a higher success rate without losing too much in the solution quality. And now the second set of experiments we did was on a synthetic domain. So we have a 2D grid world here, and then the colored regions correspond to areas where we have artificially high edge evaluation times. And we test our algorithm in comparison with lazy weighted A star for different values of the edge evaluation time and different edge existence priors. So in this plot, gray corresponds to our algorithm, and the brown is lazy weighted A star. So on the left, I'm showing you the planning time for an edge evaluation time of 500 milliseconds. So what we can see here is that we can find solutions much faster than doing lazy weighted A star. At the same time, if the edge evaluation time was lower, if it's only 100 milliseconds, then we don't quite get the same benefit. And that's intuitively because the overhead of doing ESP star and AE star is not worth it when the edge evaluation times are small. So the other interesting thing to note here is that if the edge existence probability is either low 0.25 or high 0.75, then the planning times are small. But if it's 0.5 in the middle, then the planning times tend to be larger for both of the methods. And intuitively, that's because if the entropy of the distribution or the environment is small, then we can make use of that information to plan better. So that's the sort of experiments. And in summary, what we presented was an algorithm to accelerate heuristic search on graphs where we have existence priors for edges that are time consuming to evaluate. And so to do that, we presented two algorithms. One was ESP star that generates a set of paths from start to goal and can compute the expected shortest path cost. And the second one was this anytime edge evaluation algorithm, which introduced this idea of an optimal anytime behavior, which is minimizing the expected suboptimality bound over a randomly chosen interruption time. And we showed that we can obtain significantly better success rates for this high dimensional motion planning problem. So for future work, we plan to extend ESP star for the bounded suboptimal case where we don't need all the paths. And the second extension that we want to work on is generalizing AE star for arbitrary distributions of the interruption time rather than assuming a uniform distribution. And finally, it would be worthwhile jointly reasoning about edge evaluation time as well as search instead of doing it in a stage-by-stage basis. Thanks, and I'll take any questions. Right.
Questions?
So I guess the standard question whenever your group does one of these crazy things is, have you compared this against one of the more sampling-based planners? That's the more generally what sane people think is a reasonable way of dealing with 11-DOF robots.
Right. Yeah, so in some of the earlier work on like multi-heuristic A star, for the same domains, we have comparisons with RRT star, RRT, PRM, and the whole suite. And we tend to see that the solution qualities that we get from our method are usually much better. And in especially domains where you have these tight, narrow passages that the doors you have to get through, then the sampling-based planners tend to have difficulties because there's no heuristic guiding them through these narrow passages. Yeah, so there's an extensive set of results comparing with sampling-based methods. Yeah.
Any other questions?
Yeah.
Does this notion of optimal anytime behavior depend on some finite interval that you're considering for when they'll be interrupted?
Right. So in this, we're assuming that the interruption time is randomly drawn from a uniform distribution from 0 to some large capital T, by which we are guaranteed to have solved the solution. So the thing is, uniform distributions cannot be defined for infinite support. I think something more like a Gaussian, where you have an expectation of how long the algorithm is expected to run, would be a reasonable extension.
Did you try on another one, like exponential or something like this? Gaussian is not going to be perfect if you don't want negative values, but yeah, you can.
Right. So
like exponential or something like this, did you try?
Yeah, no, we haven't derived the MDP. So what would change is that the cost for the actions would be a function of the time at which you arrive to the state, and so you can derive it for different distributions basically, but we don't have it in the paper. Yeah.
Okay, if there's no more questions, let's thank the speaker again.
Thank you.